A quantum computer is achieving computation using 0 and 1 or something in between using quantum properties. So quantum level at electrons, lights, they all behave certain way. Use that properties to create your own switches. If you can create a computer of all the switches based on quantum properties, that is a quantum computer. So I can give you an example. Everyone have done basic chemistry here, right? And hydrogen atom has one electron. So there's only one orbit outside the nucleus where the hydrogen atom is. The first orbit is called the level 0 orbit. If you heat the hydrogen atom, excite the hydrogen atom, the electron get excited and jumps to the next orbit. Correct? So that is orbit number level 1. So if you excite the hydrogen atom, it goes to level 1. If it is in the ground state, it comes back to level 0. But atoms, electrons are quantum particles. It means in reality, it is not in 0 and 1. It is a combination of 0 and 1. If you really ground it, if it is cold, it will be in 0. If it is excited, it will be in 1. But it can also be at a stage where it is in between 0 and 1, or it is both at 0 and 1. So that is the magic part of quantum physics. In the classical world, a bit is 0 and 1. A binary number is 0 and 1. Right? All of us know that computers are binary, zeros and ones. So at the lowest level, computers speak 0 and 1. That is what a classical world is. In a quantum world, it can be 0, 1, and both 0 and 1 at the same time. So what does this mean? What does this mean? It is both 0 and 1 at the same time. There's one way of interpreting is, we don't know if it is 0 and 1. But when we look at it, we'll know if it is 0 or 1. With some probability, I can say it is 0. With some probability, it is 1. This interpretation basically means that ideally it is either 0 or 1, but not that we don't know. Only when we look, we know it. But quantum mechanics, we don't go into that, go in a different direction. It says it is not that we don't know if it is 0 or 1. It is both 0 and 1 at the same time. Let us assume that I am trying to guess a 2-bit number. A 2-bit number is, every number is a bit. So 0, 0 means 0. 0, 1 means 1. 1, 0 is 2. 1, 1 is 3. So imagine that there are 0, 1, 2, 3. And the program is to guess a number. I want to crack your password. Your password can be 0, 1, 2, and 3. So if it is 0, 1, 2, and 3 on your luggage bag, first I will try 0, try to open, it doesn't open. Then try 1, 2, 3. That's how you try to guess, right? So let us see in a classical computing, that is what exactly we do. We will first try both 0 and see if it is the correct answer. If not, we'll try 0 and 1 and see if it is the correct answer. If the luggage bag opens or not. Then I try 1 and 0 and see if the luggage bag opens or not. Then I see 1 and 1. And only one guess out of this 4 is correct. So I will repeat this again and again and again. Anyone who has luggage bag and forgot their 3-digit number, know the pain. It has happened to you, right? It has happened to me. I forgot the number. Keep doing it, you cannot open. But if you had a quantum luggage bag, probably the problem could have been solved. The 2 qubits, we can put the number that we need to guess, we can put either in 0 or in 1, or we can put in both 0 and 1 at the same time. The first bit is both 0 and 1. The second bit is both 0 and 1. So which means when you combine these 2 bits, these 2 bits are 0, 0, 0, 1, 1, 0, 1, 1 at the same time. At the same time, it is all these four states. Definitely one is correct. Definitely one of the answer is correct. So if I give this to the luggage bag, is my qubits holding the correct answer? The qubits are holding the correct answer. It is holding a lot of wrong answers, yes, but it's also holding the right answer. Correct? And the bag opens. That's exactly what happens. Or that is what we think. That's what happened. So the power of this is something that we cannot even imagine. So with 500 bits, if I say that I'm going to give you a hard disk which is as big as 1 MB or 1 KB, will you be happy? You cannot even have a picture with 1 KB. 1 KB is 1024 bytes. What if 1024 bits is nothing? So with 500 classical bits, I can store 62 bytes of information, which means I can write one sentence with 500 bits. That's all I can do. But 500 qubits, if I have a qubit is quantum bit, if I have a 500 qubit, the storage capacity, information storage capacity of that is 2 raised to 500. 2 raised to 500 is more than the number of subatomic particles in this universe, in the non-universe. But there is another theory called the many world theory, which says when you open the box, you may see the cat is dead, but it is not collapsing. What happening is the universe splits into 2 universes. In one universe, you open the box and you see the cat is dead. In another universe, you open the box and the cat is not dead. So you are entangled with this, the quantum state. So this is called a many worlds theorem. The world is quantum, right? So if you're trying to create a new atom, a quantum computer can make a new atom much better than a classical computer because it can emulate electrons, protons, atoms, molecules easily. Okay, so we have diploma holders from Singapore. We have junior college students from Singapore. We have international students from different streams. We have students from IB, we have students from CBSE, Cambridge University. So we have different international students coming in. However, the majority are, 90% of our students are poly background students. And because of that, there is a learning curve for A-level students or students coming from a junior college or equivalent stream. But we have very good, bridging practices, and students usually, catch up. Yeah, so international students can apply.